Sorting. So we just went over the accumulator pattern, which is this, which adds up numbers. So now pi is this really special number, right? To get it, we have to import math, I believe, which has all the fun mathematical functions, like sine of 180. Math of sine. What about math of sine of math.pi? Math of sine 0 gets me 0. Math of 1. So what is the question is, is this going by radians or what? I don't know. I'd have to look at the documentation. But math.pi stores a value. 3.1415926 and so on and so forth. A lot of decimal places, right? Now, when you were in grade school, you probably learned pi's value is 3.14. And then maybe you bothered looking it up, or eventually you learned, hey, there's actually a lot more digits to pi. And then eventually after that, you eventually learned, actually, there's infinite digits to pi, right? It is in what we call an irrational number, meaning that it continues on and on without pattern. So the question is, how in the world did we go from 3.14, then to 159, 265, and so on and so forth? How in the world did we get there? How did we get all those digits? Now, again, let's go ahead and just check out what pi is. The mathematical constant pi is what? What is pi? Anyway, other than this number that we have to use when we deal with circles, right? It is the ratio of the circumference to the diameter. So the difference, so it is the ratio of how wide the circle is to basically how wide it is across. And actually, this is a great animation showing it, right? Here's the circle. Boom. And if you unravel the circle, it comes out to basically 3.14 circle lengths, right? If you unravel if you unroll it, a circle gets to about 3.14 circle lengths, no matter how big this circle is, right? This visualization kind of makes sense for people. It's the ratio, again, of the diameter, which is how wide it is, to the circumference. So, and it turns out that getting there, figuring that value out is a bit difficult. Ooh, it's got an entire article on memorization. Now, it's infinite, but again, decimal numbers only have a finite kind of length that we can store in them. Right? So this is probably as good as you need. But again, the question is, how do we get it? Right? How do you get it without a computer or anything like that? Ancient civilizations required fairly accurate computed values to approximate pi for practical reasons. And there's that word, approximate. So I'm going to just go back to our circles for a second. If you remember when we were dealing with turtles, right? Here with when I had Bob the Turtle draw a circle, right? I had the option of saying how big I wanted it to be, how many steps I wanted to take, and then how many sides it had. Right? And if I said I wanted to draw a circle but I only wanted to do it in 12 steps, it would draw a dodecahedron, I believe. I think that's 12. Whatever, but it basically draws a figure with 12 sides. And if we add up the perimeter of this regular polygon, if we add up the sides and compare it to basically the diameter of this, the amount of distance it takes to get across from here to here, that gets somewhere close to pi. It's not pi, but it's getting in the right direction. And the idea here is that as we increase the shape, the length of these sides adding up compared to how much it is across starts to get closer and closer and closer to that actual value of pi. So again, much like how if I tell this turtle to draw more and more sides, it starts looking more and more indistinguishable from a circle. So the answer is that pi never really had to be calculated, to exact amounts. It just had to be close enough for it to work for our calculations. So there's a lot of approximations for pi. Let's see. Chinese mathematics. Let's see. Where was that value? Early history. So Egyptians claim that. So Egyptologists claim that they've used 22 over 7 to approximate pi for Egypt, which, by the way, says it has been met with skepticism. But what is 22 over 7? That is 3.1428, right? Which is different than 3.1415, but that's close, right? So that gets you something pretty close. Let's see. And then, here we go. Chinese mathematician Lu Hui computed pi between 3.141 and 3.142 by inscribing a 96 agon and 192 agon. In other words, he did this thing with the circle that I had for 96 sides and 192. The average of those two values was this, and he suggested that 3.14 was perfectly good enough. And Chinese mathematicians eventually came up with that 22 over 7, and then this other one, 355 over 113 to get a value of 3.14159. That's getting really close there, right? If we actually do math dot pi minus 355 minus 113, import math dot pi minus 355 over 113. Notice that that's saying it's negative 2 e7. This is scientific notation over here. It's saying negative 2 times 10 to the 7th power. In other words, it's a very small number. Very, 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 very small error. So that this number is actually really accurate. But eventually, Leibniz came up with this formula. Named after Gottfried Leibniz, German philosopher and mathematician, and he came up with this infinite series. In other words, if we keep adding this up and up and up and up, we'll get close to pi. Specifically, getting close to pi over 4. It's actually it's called sometimes called Madhava Leibniz, because it's a special case of something Indian mathematician Madhava of Sangamagrama also discovered, and Leibniz discovered it later, but its form looks nicer. But essentially, the idea here is if we add up these values, we can compute pi pretty accurately. Specifically, pi over 4, but then multiply your answer by 4, boom, you've got pi. Right? And it's saying that, essentially, if we add values, let's go ahead and Python and do the Python shell here. If we add values like this, 1 minus 1 over 3 plus 1 over 5 plus or minus 1 over 7 plus 1 over 9, and so on and so forth. So now if we do that, so if we take this value and then multiply it by 4, we get close to pi. Right? So somebody discovered this magic formula. Don't need to know why. But the idea here is that as we add numbers to the magic formula, so what should the next number in this series be? Minus what? 1 over 11. And then add another one. 1 over 13 minus 1 over 15, right? And as we get more numbers, it will start getting closer and closer to pi, right? We went from 3.339 to 3.01. So the more we add, and the reason it's going to basically fluctuate in on that value until it basically gets really close to it. Okay? So the more numbers we add, right, the closer we're going to get to pi, And this is one way for us to easily compute it, because our computer's really, really, really good at doing this kind of computation. Okay, so let's go ahead and see how to do this. So let's go ahead and do Leibniz. I think that's how you spell his name. Let's just double check. Yep, L-I-L-E-I, Leibniz. Pi. Okay, so we are going to approximate pi by adding this up. And then I'm also going to use this as a way to explain functions to you, and then I'm going to move on to nested loops after this. Okay. So the idea here is that we want to calculate pi. Pi right now is going to be equal to 0, completely rational value, but the idea is that we're going to add 1, then -1/2, and so on to it. Now the thing is that these numbers over here, there's lots of them, and I don't want to type them out because I'm lazy. So we'll do a for loop. And the question is, how many values that are we going to have to this? Now this is going to be a pretty big spike in difficulty, but it's interesting to me, and therefore I think it's going to be okay. So the idea here is that we've got pi. We've got a for loop. So for blank in range, and let's say we want to do, let's see. So for example, what does range mean here? Well, in this case, this time we did it, we had 1, 2, 3, 4, 5 terms. So that in that case, if we did range 5, we would get 3, 3, 3. So let's go ahead and stick with 5 right now. Range 5. So it's going to do 5 times. So let's do for x in range 5. What we want to do is that we want to add something to pi. So our first time through the loop, let's think this through. We want to add 1. So pi is equal to the value as currently implied plus 1. But the second time we add something, so 1, then -1, then 1. So we add, then subtract, then we add, then we subtract, then we add, then we can subtract. We could also start out with our value 1 and subtract the first time, but honestly, I think it's easier if we do this. So what we want to check out here is that basically, so if this is index 0, 0, 1, 2, 3, 4, then basically we want to add on the evens and subtract on the negatives. In other words, we want to flip from adding and then to subtracting, right? So let's just simply do something easy over here. So if x mod 2, if x is even, so x mod 2 equals 0. In other words, if x is even, we'll add to pi. We'll add to our approximation of pi. Else, if it's odd, we'll subtract from our approximation of pi. Right? This is just going to compute either 0 or 1 right now, so no worries about that. But we can test it out. Print pi. Right? So it comes out to 1, which is not a very good correct value for pi, but that's okay. Right? It ran 5 because right now what's important is like saying, can I predict what's going to happen if I run this? If I tell it to run 5 times, it's going to go, first time it's going to add 1, then subtract 1, then add 1, then subtract 1, then add 1. So add, subtract cancels out, add, subtract cancels out. Then we add 1, so we get a grand total of 1. So at least now we're doing what we know is called an alternating sum. We add and subtract, add and subtract, add and subtract. Right? Notice how this is flipping us between 2 modes, right? How it's flipping between adding every other item. by using whether we're on an even index or an odd index. Or if we're doing it even and then add. So now to get to this. So here, for 1, what this is actually a fraction, right? So if we look at adding 1, we're adding 1. It becomes easier to see if we see that the first time we're adding 1 over 1, then we're subtracting 1 over 3, then 1 over 5, then 1 over 7, and then 1 over 9. So we're going to add 1 over 1, then we're going to subtract 1 over 3. These numbers aren't going to stay still. I'm going to put in variables instead in a bit. Then we're going to add 1 over 5. Then we're going to add 1 over 7. So each time I go through this loop, each time I add a new term, or subtract as it is, I'm going to be increasing the value by 2, right? I mean, yes, it's jumping up by 4 and then 4 over here, but it's 2, then 2, then 2, then 2, then 2. So that comes out to 1 plus 2 times x. Okay, but why? Well, and first let's go ahead and test this out. So now that we've got 5, run it. 0.83, that looks familiar. And right, this is actually pi over 4, so now we have to multiply by 4 to get our answer. 3.33. So this replicated what I was doing. So why is this working? Well, again, let's think this out. 1 over 1, so if x is equal to, so x's values are going to be 0, 1, 2, 3, 4. So if x is 0, what do we have here? If x is 0, we are going to go ahead and say it's even. So we add 1 over 1 plus 2 times 0. So 1 over 1, which will be 1. Okay? Then x will be 1. 1 is odd, so we're going to go over here. Pi is equal to pi minus 1 divided by 1 plus 2 times 1, which will be 3. So we'll subtract 1/3. Then 2 will be even, so we'll do 1 divided by 1 plus 2 times 2, which is 4, plus 1 is 5. So we're doing 1, 3, 5, right? We can print it out actually. We can actually print out our values. Again, over here, what we can do is we can do print one, and this will be very interesting to show you, sep. So first off, let me go ahead and show you actually what the what does anybody know what the comma does? I think I went over that previously. Actually, I can put this outside of the loop. That would be fantastic. That means I only have to do it once. Right? So it'll be 1, 1, 1/3, 1/5, 1/7, 1/9. Right? 1, 3, 5, 7, 9. So it's going up. So printing out two things, whatever they may be, or printing out two things separated by a comma separates them with a space. So, and you can have as many as you want. 1, 1 is what we have, 1, 3 is what we have, 1, 5 is what we have, 1, 7. But that's not all. But wait, there's more. What we can do is we can learn our first thing over here, which is the separator. By default, the separator is this. It's what we call it, it's a default argument. It has something by default. Separator is equal to that. But you can actually customize. Now, we don't use separator that much. What you can do is do this. 1/1 is what we have. 1/1/ is what we, 1/3/ is what we have. And it says, the things you have separated by commas, we typically separate them by spaces when we print it out. but you can specify how you want to separate them. So, for instance, if I remove that, I can say, hey, I want them separated by slashes. Hey, I want them separated by a lot of slashes. Hey, I want them separated by, let's see. Division symbol. Can I copy paste that in? Let's see. Copy. It's always exciting to figure out whether you can actually copy paste stuff in. Yep, sure. Right? This just simply tells us how I want to split stuff up. It's useful for a test. It's useful for when you want to render stuff. It basically says this is the string I want to put in between everything. But going back to this. So now we have a way to approximate pi over 4, and then multiply by that 4, we get pi. But it's not very close. But like what I said was, you know, the more times you do it, the closer we're going to get. There's 10. Now if I bump it up to 100, 3.13, 159. Let's bump it up to 10,000. 14149. Okay, 100,000. 14159,826. Pi is what? 3.14159, 265. 26535. 3.14159, and we want 26535. It's very, it's like the numbers are ending up like in the wrong places, but they're there. All right. And, ooh, you notice that it took a little bit longer there. It does take time for this to do. How many computations did my computer just do? It just did 1 million of these. 1 million. 34159,165. All right, let's bump it up to 10 million. Incidentally, it will take about 10 times as long as the previous run. 25535. 3.14159. 26. We have 25535, and as opposed to 26. So it's getting closer. It's getting really close, like to the exact value. But it's actually close enough to use for basically any practical purposes, right? And of course, once you calculate it once, you know, you don't have to calculate again. Now, mind you, most of the time, if we want to do an approximation like this, we'd actually do it as a command instead of switching this, right? Switching the code like this is kind of, you know, it's kind of annoying. So what I'm going to introduce is something called a function. And I've assigned this basic stuff in your reading. Now, a function is the ability to add a new command into Python. So let me just go ahead and show you something simpler over here. So let's go ahead and write a new command. This command is going to be what we call the repeat function. Or, well, actually, no. Start out simpler. So this is how we define a new function, and we'll see what this does. Define say. Print hello. This message ... print then I am already ... melodramatic. Okay, so what we've done is we've added a very basic function when we've added basically a new command into Python, right? Just like the length command and the other commands we have, and the print command. This one is a specific command. The def stands for def function. The say is the name of the command, and then these are basically inside the parentheses, as we'll see, is the parameters we need to run it. Does it need to take in anything? Does it need anything, or can we just run it and it will do something? And then colon, of course, to say, hey, there's an indent coming in. And so then we've got it indented, and then it's done. And so now if I can run this program by running say, like this. And then if I run it, hello, if you are receiving this message, then I am already melodramatic, right? And I can copy this, and each time I run it, it will run the same commands over and over again, right? There we go. We've got 5 repetitions of the message. So, but functions can also do things a bit more exciting than that. Like you can do mathematical functions, right? So here's one that I'll get in that we'll see more def later. Def f of x, right? Which uses a lot of the commands that we'll learn how to use. Return 2 times x, which is just simply the Python way of writing f of x is equal to 2x, essentially. Give me an x, and I'll give you twice its value. That's what it's saying. And so now we can use that new f command. F of 4 is equal to, well, So you won't need to use any returns for any of the homework we're doing, but return is very different than print. What return does is that it gives you something out of a function, which we'll learn later. So no need to go ahead in that, but we'll see that if I put 4 in, I get 8 back. If I put in 2,000, I will get 4,000 back. And if I put in hello, I get hello back, right? Because of string repetition. So functions are pretty cool. So they're really nice to be able to use that. And what we'll see here is that, and I just want to, I'm touching them on it a bit here. You're going to learn how to use them in the homework and look over them in the readings. We'll go over them in a bit more detail because I want to still stick on this. But what I can do over here is I can put this all in a function. Def pi approx accuracy, or maybe let's call this steps because that's easier to spell and shorter. And then what we can do is put everything else inside this function. Okay. Steps. And now what I'll do is I'll replace that with steps over there. So notice that I've replaced the 10,000s with the steps over here. Now, if I run this program, it appears to do nothing. But actually what it does is that when you do this definition, this define function, what we're doing here is that Python will read this and it'll say, you're defining a new command to give me. I'll keep that command in memory until the shell restarts. Basically, you're defining a new verb, and it says, I'll keep that in mind until we restart, because if you want it to be permanently added, just simply give it to me again. So define pi approximation. You're saying, okay, this is a function, a new command, and you're expecting me to give you steps. Okay? And then when I do that, I'll say pi is equal to 0. I'll run this for loop using steps, and then I'll print out an answer. Now, it's appeared to do nothing, but notice it says restart, and then it gives us nothing. So maybe I'll just do this. Over here, print, and outside of the loop, print function has been registered. No need to actually put that in any program. This is just for demonstrated purposes only. Function has been registered. So now, actually what I can do in the REPL over here is that I can call this function like any other, because Python now recognizes it. So pyprox 5, and that's running the loop with 5. That makes it run the loop 5 times. Right? Because what I'm doing is I'm putting in 5 over here. I'm pointing to my screen. Why would you be able to see me point to my screen? I don't know. So we put in 5 over here. And then it will say, steps is 5. Okay, when I see steps, I'll remember that you mean 5 instead. And that's what it does there. So if I do 10, similarly, pi approx 10, it'll go, by steps, you mean 10. So whenever I see steps, I'll replace it with 10, because I know what you mean now. I got you. Okay? And so I can do this whenever. And if you give it nothing, it's going to flip out. Because I said, because what I did is that I broke a promise. I promised Python that if you register this new command, I promise you that when I call it, I am going to give you a parameter. I'm going to give you one thing and one thing only. Right? I'm going to give you steps. I'm going to give you the number of steps this is going to run. And it says, you're missing an argument. You're missing steps. I don't like you anymore, is what it says. So it threw an error. Now, mind you, I can still use pi approximation because I haven't restarted this yet. If I do pi approx now, and similarly, if I do pi approximation with 5 and 15, it's going to go, you promised 1, you gave me 2. Normally, giving me more of a thing would make me very thankful. But no, we're in an unambiguous science here, right? If you tell me you're going to give me one thing, I expect one thing, right? Right? If similar, like think about it this way. If I told you I was going to give you one exam in a couple weeks, and then you come in and I give you 2 exams to complete at the same time, you'd probably be very upset and also very confused. Right? Similarly, Python gets very upset and confused when you are giving it more than it expects in the command. We specified you're going to use only one thing, so you're going to use only one thing. Also, if the thing doesn't make sense for what you're putting in, this is the only bad thing about Python. It can't really detect pi approximation 100, the string. It's going to be in other programming languages, it would detect, hey, you can't do that. Here it's just going to say it's going to try its best, and then if it finds out it won't work, it will just crash. Anyway, but going on, I can now just call pyprox like this. Right, as many times as it needs, and it will run it. And it will compute a value that's close to pi. Right, and it'll print it out. Right? So again, this is the Leibniz approximation. And this is what we call an accumulator, where basically we add these values to pi. There's plenty of practice for you on these things. But this is one of the most common things we use. This is one of the most common things we use for loops for when we're not dealing with turtles and stuff, which is to add stuff up in some way. In fact, there's I think one question of your on the latest homework that uses an accumulator, but this is actually probably more complicated than anything you'll see in the homework. I like to do more complicated and then give you work that's slightly less complicated because programming's already hard enough, because the thing that makes programming hard is that you're your own worst enemy, right? All those random mistakes you make. Everybody makes them, including me, so don't worry. It's part of the process. All right. So let's go back to more comfortable territory with turtles. Okay? Right? So we're going to go ahead and create a new file called nested turtles to explore nested loops. And now, normally this is where I think a lot of students start struggling, but hopefully by using turtles, we'll be able to, we're going to be able to do this. Now, by nesting, I'm not talking about where these turtles are going to build a nest, although that would be pretty cool. Instead, what I'm talking about is that we're going to be nesting our for loops. We're going to have for loops inside of for loops, much like we have an if statement inside of for loops sometimes. No worries, it's not going to be as hard as it looks, though. Import turtle. All right. Let's go ahead and do, and let's create Bob. Let's see, so first, yeah, Bob is equal to turtle dot turtle. And then what we're going to do is, of course, turn him into an actual turtle. Bob is equal to, or Bob dot shape is equal to a turtle, and Bob dot size, or shape size rather. Yeah, shape size. Shape size is equal to 1.5, 1.5, right? And we'll just simply grow him right now, or we're going to show you right now so we get this. By the way, I just restarted Python by running a new program, so if I try to do pi approximation again, it's going to tell me it's not defined, right? The command only lasts while the program you're currently running is still registered in there. So that's okay, though. So what we're going to do with Bob is that I want to draw kind of this. Oh, there's really a lot of stuff today. Okay. Well, I don't really need anything too much for this. Really what I want to do is I'm going to do a variation on our drawing a square. We've seen drawing a square. We've seen drawing a spiral square. This time I'm going to do something a bit more interesting. Our end result is going to be a square inside a square, inside a square, inside a square, and so on and so forth for as many times as we want. But what I want to make different, and then what I want to do is make it so that each of these squares basically has a different color each side. That's my eventual goal. But for right now, we're going to just start with drawing a square using a for loop again, and build up from there. Okay? So this will go over a lot of iterations, but it's there's going to be a lot of changes to this code as we go through it. No worries. So for Bob, so for how many? There's sides. There's 4 sides to a square. So for blank in, let's just say for side in range 4, there's 4 sides, so repeat the following 4 times. Tell Bob to move forward. We're going to tell him to move forward 50 to, 50, and then we're going to tell him to move forward to rotate 90 degrees. Bob.right 90. Why am I getting a lot of text messages all of a sudden? Oh, good. Right? So kind of thin back there to see. So let's go ahead and say, so let's go ahead and do, so many things open. There we go. Bob dot pen size is equal to 2. Is that any better? Slightly better, slightly thicker, slightly more defined. Okay, so that draws a square, right? Have him move forward 50, turn right 90 degrees, have him do it 4 times. So the question is, how do we get concentric circles like that? Right? Well, the question is, how many concentric circles concentric squares do I want? I would like, well, let's start out with 5 concentric circles. So what I'm going to do is that I am going to go ahead and write this for loop over here. For num squares, or sorry, 4 square in range 5. And we're going to eventually replace these magic numbers with magic variables, so no worries. So let's take a look at what happens if I do this. Notice that I've got a for loop inside a for loop like this. Shoop, shoop, shoop. Bob goes around. So what just happened? So what we did is that this outer loop runs 5 times. And then this inner loop ran how many times? Ran 4 times each time it ran. So if you notice, Bob's going to make... So let's go ahead and just watch Bob again. 1, 2, 3, 4, 5. So he goes around and makes 5 squares, right? He repeats this 5 times. Does that make sense to everybody so far? Right? If I were to change this to 20, 3, 4, 5, 6, 7, he'd do this 20 times, right? Make sense? Now, why would he do it 20 times? This error is perfectly fine. That just happened because I killed it while it was running. Because I told it to run 20 times. Right? So a for loop inside a for loop just simply basically is nothing special. What you do is you just simply look at this command. You basically run each command each time you go through the loop. If the command's another loop, then you're going to do that loop however many times each time through the loop. So now what's interesting over here is if we do this like this, 4 plus square times 10. Let's see what happens there. Each time he made a bit of a bigger square. Right? Bob.forward. He moved forward 50 square. He moved forward 50 feet, 50 pixels, times square, so 0, and then turned right 90. So the first innermost circle was the same. The second square, not circle. I don't know why I'm saying circle so much. The second circle, did it again. Second square was 50 times 1, 50 plus 1 times 10 for a grand total of 60. So we moved 60 this way, then 60 this way, and then 60 this way, and so on and so forth. And then the second time, next time it was another 20 for 70, and then 80, and then 90. Now it ended up being like this because he ends up staying right over here each time. So let's take a look at this in a bit more, with a bit more finesse, shall we? So what we're going to tell Bob is that each time we want to draw a square, draw your 5 sides. Get slightly bigger each time we draw a square. Then, what I want you to do is put your pen up, Bob.pen up, because I need you to move. Bob.pen up. And what should I do? Now you're facing, well, you're going to be facing this way. And what we need you to do is I need you to move like this, right? I need you to move over to here, from this corner to this corner. So what we'll do is we'll just simply say Bob.right, Bob.left 90, Bob.forward, and how much should he move up? Let's try 10, or let's try 20 over here. No, let's try 10, keep it consistent. And then Bob.left left again, and Bob dot forward again. And I will slow this down. Bob dot left 180. And then Bob dot pen down. And yes, I will make this bigger, easier to see the next couple run-throughs, by the way. So, and Bob dot speed 1. 3, 4, pen up. So what's going on here? Well, I moved 10 and 10, but I'm still telling it to move 10 each time, so I'm ending up lining back where I am. So maybe if I told it to do twice as much over here, see if that would work. Really confused over here. Well, it works. All right, so first off, it's a bit harder to see. So let's go ahead and fix that. First off, let's go ahead and increase this pen size to 3. Next, what I'm going to do is I'm going to change the distance. So let's go ahead and replace a bunch of stuff with variables so that I make it to, easier to basically change this. So let's say the gap between the squares, I want it to be a bit bigger. So gap is equal to, let's say 20. Right now the gap is 10 pixels. Let's make it 20 pixels. And so what you're going to do is I'm going to replace it with gap, and then square times gap times 2, which somehow made that harder to look at, I'm sure. And then base length is equal to 100. So what I did is that I said I defined two variables. One is going to be the base length of the square. So in other words, how big our innermost square is going to be. And then the gap is going to be how big of a distance do I want between each of my squares. Because this part, what it's going to do is that I put up the pen, I have him turn, I have him move forward, I have him turn, and I have him move forward again. I suppose, actually, I can also simplify that. But there, then he turns. So the reason he does that left and then right is because this for loop over here says turn right each time, and then I have him turn left to move up, and then I have him turn left again. And then we end up with 5 circles. Let's go ahead and make this a bit easier to watch, because that looked pretty ugly. So what I'm going to do instead is I'm going to tell Bob.back gap. That way he doesn't have to turn. And then I'll have him turn just one more time, actually. Bob.left 90. Bob.forward gap. Don't have to remember how big it is now, how big the gap is, because guess what? I have it stored in a variable. And then Bob.right 90. Okay, that's a bit easier in some ways. Let's see what he does. Forward, 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 forward. Move backwards, turn up, move that way, turn back this way. Back. So now he's going through this. Now what's really cool is that I can start doing a whole lot of interesting things with this base over here. Any questions about this so far? About how the... inner for loop works, right? What he does is that we have him draw, right? For each number of squares that I want to draw, I have him draw a square, and then I have him adjust his position to draw the bigger square. So let's go ahead and basically have a bit more fun. Let's go ahead and just simply for the sake of speed, turn up the speed a whole lot. Let's go ahead and say num squares is equal to 10. And what we'll do is that basically by putting my variables over here, I make it a whole lot easier to change the program just by messing in one place. And let's change the gap to 15. Okay. Now how do I make it multicolored then? Well, let's go ahead and do that. Side colors is equal to, let's go with stuff that we can define as unicorn vomit. So for in other words, like cyan and pink, you'll understand what I mean. Yellow, what's another one? Any suggestions? Beige would be in there. Maybe some green. All right, so there we go. And what we're going to do is that say, rather than doing 4 side in range 4, what I'm going to do is 4 color in side colors. Right? How many side colors are there? There's 4, so it's going to run the exact same number of times. Right? So, and now what we can do is we can say bob.color is equal to color, is set to color. And now, there we go. Looks like a printer that's out of ink. Right? We're doing an ink test. So we've got cyan, pink, yellow, and green. Any better suggestions than green over there? I'm open to suggestions, but okay, we can keep it for right now. But anyway, we've got 4 colors there. So there's a lot of interesting ways we can take this. Let's start out by what if I wanted to add another color? What if I just didn't want to do, one color or not? What if I wanted to do what would happen if I added another color? Let's say red over here. Oh, that's interesting. What in the world happened there? Well, let's go ahead and comment out side colors, copy it, and replace it with all with black, or at least all with the same color. Cyan, 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 cyan. For right now. So what's going on here? So doesn't seem to draw any differently, not really, except he ends up over here rather than over here. So now because side colors is 5, right? What is he doing? We're drawing a square like this. 1, 2, 3, 4, 5, ending up over here, and then facing down this way. So that starts as our new position over there. And then from here, I would be doing 1, 2, 3, 4, 5, and then starting from my position over here. So going around an additional time by adding an additional color like that, which is interesting. Very, very interesting, especially since it gets this really interesting thing where we are kind of alternating the colors as we go around, right? Let's go through this a bit much slower. So first, oh, that's not much slower at all, right? Change the speed to 1 because it's weird like that. So cyan, pink, yellow, green, red, back up, go around. Cyan, pink, yellow, green, red. So all the cyan essentially. Pink, red, green. So we've got all these nice pastel colors over here, but we noticed that basically that it's just overriding that thing, which is okay, because I just wanted to do that for experimental purposes and see what would happen. So again, just because it's squared doesn't necessarily mean it's going to follow exactly what we're saying over here. The only problem I had with like doing the side length like this is that, you know, we had the issue of what's going on over here is that it's colorful, yes, but everything's on the same side. It'd be really cool if we could like rotate that a bit each time, right? What do you think? Like getting the colors to shift so that the cyan starts over here, then it's over here, then it's over here, and so on and so forth? That would be really cool. What do you guys think? Yeah, mild interest of mild interest that you're showing just because you're sitting here and would rather be watching, I don't know, Game of Thrones because everybody says you should have totally watched it when it was out. Anyway, let's see. So let's go. So what we can do is that, right? So there's two ways to go about this. One is to do something interesting with the index over here, right? I'm going to show you what I call the easy way and the hacking way, I guess, or sorry, the messy way and the hacking way. So range, length. So actually, let's go ahead and do enumerate. Actually, there really is no easy way to do that. Oh, yeah. Yeah, for range length side colors. So I'm going to just show you two ways. You can decide which for yourself is easier. So over here, we've now switched this into an index loop, right? For each index in the side colors, right? What is the length of side colors? It is 4. So for each index in there, we're going to go through 0 through 3. And I'm going to say color is equal to index, right? If we say color is equal to index, we get no change whatsoever. Oh. Type of object int has no length. Oh, right. Color is equal to side colors index to get the ith item from there. Everybody remember that notation? No? Yes? Boom, boom. So it's no change whatsoever over here. But now if I do like side color, this is going to scare some of you, but that's okay. Like I said, I'm going to do this one way, which I consider to be a bit kludgy, and then we're going to use Python's awesomeness to our advantage over here. Side colors, index plus square. So what square are we on, plus the index. Now normally that would get us out of range, but what I'm going to do is I'm going to mod it by the length of side colors. In other words, I'm going to mod it by 4. And that should look ugly because it looks ugly to me. But let's see what it does. It's starting to alternate them. How is it doing that? I ask knowing the answer, which is that what we did is that each time we so basically index is always 0, 1, 2, 3. Each time we go 3 through, but square is going to be different. So square starts at a 0, so index plus 0 is mod by the length of this, mod by 4. It's going to be 0, 1, 2, 3. But the next time we do this, 1 index is going to be 0 plus square, which is equal to 1. So we'd be starting at pink that time. Then we'd be going to yellow, then to green. And then eventually we'd have index 3 plus square, which would be 4. Mod by 4 gives us 0, which wraps around. And if you think that's kind of complicated, yeah, I can only do that because I've been doing this for a while, and I only really got comfortable with that after a couple of years of actually saying, yeah, I can program. So no worries if that looked utterly scary and horrifying and totally intimidated you, because it would have intimidated me too, and it probably intimidated a whole lot of your classmates. The other way to do this is that we can use list slicing and concatenation to modify this. Right? What we can do is we can take the first item and move it to the back. And so let's go ahead and do that. So to modify our colors. So first color is equal to, what is the first color in that list? Not cyan, but I mean like literally any iteration of the loop. The first color in the list is going to be side color index 0, right? And then the other colors, all the other colors are going to be the slice. So this would be index 0 is the first color, other colors, right? That makes sense to everybody? I'm going to separate this into two lists, or rather two things. Side colors, or rather, we've got side colors, the first item in there, and then we can do this slice over here. Other colors. Side colors, 1 through to the end, right? So now, if I do, and if we, let's go ahead and print this out just to say, well, let's actually not right now. First colors. So now, let's see if this will work. First off, first thing to note, though, this will get me an int. This will get me an int. Sorry, this will get me a string. This will get me a list, right? String because it's a single item. List because it's a lot of items. And if I try to do like hello, oops, right? If I try to do hello plus world, a string plus a list, nonsense, can't do that. But on the other hand, if I have a list and a list, I'll get hello and world. So there's two ways to deal with that. The first is that I can use this notation, which says, I'd like a list of one item, put it in here, please. Okay? The other thing I could do is I could use a slice over here and say, slice me for everything from 0 to 1, and that'll give me a small list. So everything from 0 to 1, not including index 1, and everything from 1 up to the end. And then what we do is we say side colors is equal to the other colors plus the first color, right? In other words, the other colors go first, and the rest of the colors go to the end. Now if we run this, now we swap the colors. Oh, name side color is not defined. Colors. So now we move cyan to the back. Cyan's last. Now we move pink to the back. So yellow's the first color, and pink's now last. And we move yellow to the back, so we've got green, cyan, pink, and yellow. Now cyan's the first color again. That is an excellent ringtone choice. All right. Speaking of dances, let's go ahead and see what we can do by getting. Now that we've got this rotating, let's go ahead and make this a bit more psychedelic by making it a different shape. So we're going to add red over here, but I want something with 5 sides. So we're going to do what we did last time, and I'm going to divide, instead of rotating right by 90 degrees, I'm going to go ahead and rotate right by 360 degrees divided by length of side colors. Divide over here because I think I need an integer. And now, this should automatically adjust to being able to draw a pentagon. And we're still doing the rotating color thing because we still have that code in there. Now, what did that code do? It said rather than rotate 90 degrees, rotate a fifth of a full, rotate a nth of a full circle, where n is the number of colors you have. So the number of colors will be equal to the number of sides, right? If I add one more color, it's going to be a hexagon. Why? Because this will run n number of times, or this will run the number of times there are side colors. So 0, if I do is teal a color that we can do? God, if I know. Yeah, apparently. So we can totally do very, very colorful patterns over here. And now let's go ahead and see what happens if we leave out some interesting parts, such as the pen up part. We get a little jagged thing over there. But notice that the for loop inside the for loop really didn't become the most complicated thing in this, right? What we're saying is that basically a for loop and a for loop means that basically we want to repeat something multiple times as part of another repetition, right? For each square that we're doing, we need to draw each side, right? It's like going through each, right? Suppose you have a paper you're reading, right? It's like saying for every word on this, for every page in the paper, for every word on the page, right? It doesn't necessarily have to be too complicated. So when we get back on Thursday, we are going to leave off on turtles for a lecture, and we're going to learn plenty more about how to do nested for loops. Oh, and one last important announcement, because it's about time to start thinking about exams for us. So our first exam, I think it might be a bit too soon if I try next Thursday, because I'd rather have you guys have mastery of for loops and the like. So I'm probably thinking that it will be our first exam will probably be October 3rd. And we will do the exam in lecture. That way that nobody has an unfair advantage or disadvantage as opposed to timing for it.